Good afternoon, gentlemen. Today is Tuesday, April the 21st, and today we are going to talk about something called damped oscillations. Now, last week, or well, the week before the Easter break, we talked about the idea of an oscillating spring or even a pendulum, all right? And, as a pendulum swings back and forth, we know that according to all of our calculations thus far, the oscillations never slow down. They never change. They're uniform, and they do this in perpetuity. In reality, that's not really the case. Every pendulum will slow down at some point. If I just let this swing for a while, even even now, you can see that it's beginning to slow down a little bit, and eventually it will come to rest. All right. This is what's known as a damped oscillation. All right. And so a damped oscillation is one that runs down and eventually stops. All right. And this is by far a more common type of oscillation. In reality, a spring or a pendulum or that sort of thing is always going to slow down. For a pendulum, the main reason that it slows down is because of air resistance and possibly even friction at the point where the axis of rotation sits. All right, but air resistance or drag force and friction will eventually slow it down. Now, as an oscillation decays, in other words, slows down, the rate of decay also slows down. All right, so it's twofold. And what that means is that any math that's involved here is going to be an exponential kind of thing. It's a decay of a decay. All right, we'll get to that in just a moment. But the moral of the story here is that if you're looking at the successive peaks in an oscillation as it slows and slows and slows, the difference between successive peaks is going to be less and less. So, what does this mean for us and our work here? Well, first, the damped oscillation causes the maximum amplitude to decrease with time. So if you look here, all right, this represents the maximum amplitude in graph A. All right, and the change in that oscillation is the difference in what we call X max, and that's this right here. All right, and if you look at the difference here, from here to here, and from here to here, and so on, you'll notice that way down here, there's a very tiny delta X max, a very small change in that oscillation. Whereas at the beginning, there's a very large change or delta in that oscillation change. Now, the formula to calculate this is the one that's shown here, and this is an ugly looking formula, but it essentially says that the change in amplitude is going to change based on, the original amplitude, A, times E, which is the base of the natural logarithm, ln, ln in math, maybe. I hope you've learned some of this. Times the exponent value negative t over tau. Now, negative t, or the t, simply represents the time that's gone by, and that, darn it. Sorry, fellas. What is going on? That t is, I'm sorry about that. This mouse is not doing things that I want. But the t is the value on the x-axis. The value tau that you see here is what we call the time constant. All right, the time constant. Now, the relationship here, if you compare the displacement versus time graph, you can see that the relationship between A and E, the natural log, and this value tau is shown here by this XY relationship. And so that time constant tau is the time that it takes for the maximum displacement to decay to 1 over e of its initial value. So that's why we have the value a divided by e on the y-axis and tau on the x-axis, okay? Again, this is some kind of ugly math, but it's something that those of you in calculus, especially those of you in AP calculus, should be pretty familiar with, but I'll just keep my fingers crossed for that. Whoops, gonna have to ignore that phone call. Now, let's have a look at the relationship here. We've got the exponential decay occurs when a quantity y is proportional to the number e taken to the power negative t over tau. All right, tau is the time constant, and we write the formula as this, and you can see that here. Now, here's a over e, and here's the value of tau. But look what happens when we square the value of the natural log. That takes us all the way out to 2 tau. All right, and so the relationship is, if this is e to the 1th and this is e to the 2th, that shows us a method of calculating the value of tau. So whenever t increases by 1 time constant, 1 tau in other words, y decreases by the value of 1 over e. So at time equals 0, the value of y equals a. But if we increase time to the value tau, then y decreases to a divided by e. If we increase t to 2 times tau, then y is reduced again, another factor of 1 over e, to a over e to the 2nd power. And so, in conclusion, we can say that at t equals n times tau, y has the value a over e to the nth power. And so what that means is that as time becomes very large, the value of y, or the amplitude, the change in amplitude, becomes very small and approaches 0. Those of you in calculus should recognize this as the basis for calculating a limit. And that's essentially what we're doing here. We're calculating the limit of the amplitude. So, mathematically, the oscillation never ceases. All right, it's always there, but it's very, very small, to the point where it actually becomes undetectable. It's simply a vibration rather than an actual oscillation. For practical purposes, the time constant tau is the lifetime of the oscillation. In other words, the measure of how long it will take to decay. If the value of tau is much less than the period, then the oscillation persists over many, many periods, and the amplitude decrease is small. In other words, if the period is a very long period, the change in the amplitude will be exceptionally small. However, if the period of the oscillation is very small, like in the second case here, then the value of tau will be much, much larger, and therefore the swing or the oscillation or whatever it is will dampen very, very quickly. Okay, so bigger period things will undergo many more oscillations. Very small period oscillations will damp very, very quickly. Okay. Now, your homework, gentlemen, for this evening is to do homework questions 35 to 39, odd numbers only, in section 14.6 in your textbook. Okay. Happy Tuesday, and I will see you tomorrow.